Hello everyone, we are from Chemical Engineering and we will be presenting our critique on the effects of carbon dioxide water rock cycling cycles on sandstone pore structure. So, in summary of the article, the first, the primary objective is to determine how verifying hydrochemical environments, which is sulfate-rich versus chloride-rich brines, influence rock stability under repeated carbon dioxide water rock interactions. The experimental conditions of this experiment is 14 degrees Celsius and a pressure of 5 megapascal. The saturating fluid tested are sodium sulfate and sodium chloride and pure water. So what are the key findings? The key finding is the sodium sulfate solution caused the most severe dissolution of carbonate and feldspar minerals, leading to the greatest increase in micropore volume and largest decrease in acoustic wave velocity. Moving on to my evaluation of the research question, one of the major strengths of this study by Huang et al. Is how exceptionally well defined its scope is. In a field as complex as carbon capture and storage, it is very easy for a study to become too broad by simply looking at general interactions within carbon dioxide and reservoir rocks. However, these people deliberately avoid that trap. Instead of a generalized approach, the authors pinpoint specific variables that are highly pertinent to our real-world CCS operations. They focus strictly on two key factors: the cyclic nature of the carbon dioxide injections and the distinct ionic positions of the native brines. Explicitly comparing sulfate-rich brines against chloride-rich brines, they create a very narrow, highly focused, significant strength for the scientific inquiry. By narrowing the scope, they clearly define the objective of the experiment and isolate the exact variables driving rock deterioration. Ultimately, this allows them to draw much more definitive and actionable conclusions about how specific hydrochemical environments impact geological carbon sequestration, which is far more valuable than a generalized overlay. Moving on to their methodology, the experimental design is exceptionally well suited for studying complex multi-phase flow in porous medium. A major strength of this study is its dual methodology. The author used NMR to track physical changes in the pore structure, while simultaneously using ICP-OES to measure the chemical mineral dissolution. Additionally, by using a controlled core flooding apparatus at 5 megapascal and 14 degrees Celsius, they successfully isolated the chemical variables from any thermal influence. However, there is one slight drawback to note. These pressure and temperature conditions are relatively low because they do not completely replicate the intense thermodynamics of actual deep subline aquifers. This could have some impact on the real-world reaction kinetics.
First, we take a look at the validity of results. The methodologies used are geochemically sound, combining NMR scans for pore space, liquid chemistry testing, and wave velocity to track rock strength. In the chemical data, we see an initial spike in calcium and magnesium as acid rapidly dissolves calcite, followed by level concentrations as new minerals form. This matches standard chemical thermodynamics. Lastly, the data proves sodium sulfate brine is more aggressive than sodium chloride brine, as sulfate ions react with calcium to form insoluble crystals that clog large pores. Moving to data interpretation, the NMR data reveals a two-way convergence mechanism. Large micropores shrink from mineral clogging, while small micropores expand from acid dissolution. This dual process forces both large and small pores to meet in the middle, making mesopores the dominant pore type. There were some minor limitations, such as sample drying causing slight damage to artifacts, and the short 16.5-day duration limiting feldspar dissolution. Overall, the main conclusions on rock degradation and brine impacts still remain completely solid and valid, even with those limitations.
I'll be talking about the limitations of the study. Firstly, the small core plugs used don't have the same heterogeneity and complex regional stress regimes found in deep saline aquifers, the dissimilarity of the subsurface chemistry because of the use of single salt brines and only one type of sandstone, the short period of study which does not account for multi-decadal geochemical equilibration and reactive transport dynamics, and the lack of 3D microimaging or dynamic permeability measurements for investigating microstroke clogging, flow pathway tortuosity, and transient injectivity impairment.
Now I will be talking about the significance and relevance. We have broken the significance of these findings into four key pillars. First, this study is highly relevant because it moves away from static models and simulates the actual cyclic pressure changes seen in industrial carbon storage. Second, for chemical engineers, it maps out how secondary mineral precipitation chokes major fluid pathways over time, which is critical for predicting long-term reservoir lifespan. Third, it gives geologists a clear chemical blueprint for site selection, proving that we should avoid sulfate-rich aquifers because they clog much faster than chloride system. Finally, it provides a non-destructive safety metric by linking this pore damage to drop in acoustic wave velocity, allowing operators to use seismic tools to monitor the reservoir and prevent caprock failures.
Moving on to ethical concerns and our overall conclusion. On ethics, this study is fairly low risk. It only involves low rock samples and synthetic brine, not human or animal subjects, and the authors properly disclosed their funding and declared no conflicts of interest. That said, we noted two gaps. The paper doesn't fully address the safety implications of applying these findings at real storage sites, and the sample size is small, which limits how generalizable the results are to actual reservoirs. Overall, we found this to be a solid, well-executed study. The authors used three different methods, NMR, ICP-OES, and wave velocity, to build a consistent picture. Sulfate brine damage pore structures the most, followed by chloride brine, with pure water having the least effect. This is genuinely useful for site selection in real CO2 storage projects. However, the experiment only ran for 16.5 days, while real storage operations happen over decades. So while this is a strong mechanistic study, it's not yet validated on a field scale.